So we'd introduced the idea of radio telescopes and radio observatories. And the problem that we end up with radio telescopes is that radio waves are very long wavelength, which means the radio telescope has to be huge in order to function just as well as a small optical telescope. In fact, the radio telescope, in order to see as well as your eye, has to be almost the size, of miles across. And that's because that the radio telescope, as light is coming into the radio telescope, the radio waves are coming in from a big patch of the sky, so you're not able to tell exactly where the signal is coming from. So unlike with optical telescopes, where you can see the exact spot the light's coming from, radio telescopes really tell you just the part of the sky it's coming from. And that's not good enough really for astronomy. So what we do is we use something in the physics of waves called interferometry. Okay. So if you have two waves, and these two waves are completely in sync with each other, when you add them together, you're adding peak to peak and trough to trough. So the ups are more up and the downs are more down, and you end up with a really big wave. But if the two waves are 180 degrees out of sync with each other, then the up of one is matching with the down of the other. The down of the first one matches with the up of the other one. And so we add up and down to down, you end up canceling everything out. So we call this constructive interference or destructive interference. They're both called interference. So wave interference can be either constructive or destructive. And in this case, we can have one or we can have the other. Now this is where it comes in useful for radio telescopes. For a radio telescope, then you can have two radio telescopes pointed at the same thing. So two radio telescopes pointing off at the same object, and the signals come into both of them simultaneously. And so then electronically, the signals can be brought together and added. So if you had two signals that were like that, so the two signals were like this, so they add together. Now, the thing, though, is if you start looking off to the side a little bit, so you start looking off to the side, if you tilt this a little bit, you notice that, oh, wait, the peak of one is balancing up with the trough of the other. You tilt it a little bit further, and the peak of one balances with the peak of the other. And so that means that the two radio telescopes here point at the same thing, even though they're not super precise in terms of where they're pointing. If what you're looking at is slightly off, you get destructive interference, you don't get a signal. So that means you can more easily tell where the signal is coming from. Well, the farther apart the radio telescopes are, the farther apart they are, the less of a tilt it takes until they tend to cancel each other's signal out. That distance apart we call the baseline of the interferometer. A system of radio telescopes put together is called an interferometer. And so the farther the baseline is away from each other, then the more precise the triangulation is, and the more precise that you can get the actual size, actual position of an object in space. So this is what we want to do, is use an interferometer. So with an interferometer, those two radio telescopes work just fine, but you can do better than that. You can have 3, 4, or 5 radio telescopes going. And if you have several radio telescopes, that's an array. Now, technically, a two-element array is just your simple interferometer, but you could have a 3, 4, 5, 20-element array. And so these large arrays tend to be much more precise in terms of triangulating. And the other thing is, by interconnecting one radio telescope to another radio telescope and doing it in a sequential fashion as the Earth rotates and changes the vantage point, then you can use a computer to synthesize an image and to synthesize the effect of a giant radio telescope. So if your array is stretched out over 20 miles, then you could synthesize a radio telescope with a diameter of 20 miles and get the resolution of such an instrument. So several large arrays were constructed, and eventually, using money from the National Science Foundation west of Socorro, New Mexico, they built a very large array. And the name of this facility is the Very Large Array. Now, in recent years, they did rename it the Jansky Very Large Array in terms of honoring Jansky, but the Very Large Array is this radio observatory west of Socorro, New Mexico. And it consists of a number, almost 24 of these giant radio telescopes. Now, each of these radio telescopes is 85 feet across, to give you an idea how big these things are. Each one of them is a separate little structure that can be picked up and moved around. So they can actually pick these little railroad tracks run along there, and they can pick them up and move each one around along this big Y shape that can stretch out for dozens of miles. And so you can bunch them up close together, or you can stretch them out a long way away. And so by rearranging them, you get different kinds of sensitivities and different kind of resolutions. So they'll range them one way and run it that way for about 4 or 6 months, and then they'll rearrange it for a different way and run it for 3 or 4 months, and so forth. And so the Very Large Array, and each one of these dishes is 82 feet across, and each one weighs 130 tons, and they may be picked up and carried around. And that's actually a picture of me standing right there, about 100 feet in front of that radio telescope right there. Again, this gives you an idea as to how big these different structures happen to be. And imagine just having a machine that slides up underneath here and picks it up and carries it off and sets it down somewhere else. Very Large Array is one example, but the thing is, unlike a little small array in which the radio telescopes are connected together with wires, the Very Large Array, each one is a standalone instrument that collects the data, and they use computer processing to put it together to make an image. By the way, very similar computer processing was adapted from radio interferometry to use with X-rays that look at the body from different angles and put all this information together to make a 3D picture. That would be, for example, a CT scan, or if you use magnetic resonance and microwaves, that would be an MRI. And so these are different technologies that use very similar computer software adapted from what was originally for radio astronomy. But because each one of these things is separate, all that you need to know is the center of one to the center of the other to within a fraction of an inch. That's very difficult to do, but it can be done as long as they're all close to each other. Well, we now have the technology to find the distance between one radio telescope and another radio telescope hundreds or even 1,000 miles away to within a fraction of an inch. And so that means we can have radio telescopes stretched out across the Earth. And so that would be a very long baseline. So such a thing we call the Very Long Baseline Array, VLBA. And so there are VLBA facilities stretched out across the Earth. So that would synthesize a radio telescope almost the size of the Earth. One of these VLBA facilities is actually at the base of Mount Locke in far west Texas. Mount Locke is where the McDonald Observatory is. If you take a tour of the McDonald Observatory, then one of the things they like to do for the tourists is to take them to the edge of the mountain, and standing there you can see this radio dish down in the valley, and then you see a bunch of domes for the telescopes. And the tour guide always asks the visitors, how many telescopes do you see? And they point to the number of domes. They say, well, I see 4 domes, so that's 4 telescopes. And she goes, oh, no, that's not right. Those are domes. They're not telescopes. And they go, oh, none. And then she points down the valley and said, there's one right there. That's a radio telescope. We went there a couple years ago with some of my students, and we'd already had this lecture ahead of time. And so what happened was that she took the group over to the edge of the mountain and said, "How many telescopes do you see?" And she was going to be all proud of herself by telling them that when they pointed at the domes, that's not a telescope. And so instead, all my students pointed down to the radio dish in the bottom of the valley and said, "There's one right there." And so that kind of deflated her. But anyway, so there we have the radio telescope VLBA at the McDonald Observatory. Now the question that then comes up is, what about optical interferometers? Now the problem is you would need to know the position of one optical telescope to another optical telescope to within a fraction of the wavelength of light. That would mean you would have to know the center of one telescope to the center of another telescope almost to the width of a virus. That's very hard to do, but not impossible. The Keck telescopes, Keck 1 and Keck 2, are actually designed so that you can take the light from one of them and the light from the other one and then mix them together in a facility underneath down here and a light lab under there. And what it does is it will act like one big optical telescope of that size, much bigger than either one of the telescopes. And so the European Southern Observatory built a facility that is 4 individual large telescopes. They can look at 4 different things, or they can all look at one object, and so they all look at the same object up here and combine all the light together to one place and act like one very large telescope. And so what would you call such a facility? The Very Large Telescope, obviously. And so the Very Large Telescope is the name of this group of 4 telescopes that can occasionally act as one big telescope. There's in Arizona, there's also, they built something that was 2 big mirrors that focus together in one spot to act like one big telescope of that size, and they call it the Large Binocular Telescope. And the ultimate goal, what we would really like to do is have like a constellation of space-based radio or optical receivers that connect together. Now we have put radio telescopes in space that have been linked to the Very Large Array to Earth to make an even larger array. And so that would be something that has an effective aperture even bigger than Earth. But we could imagine that we could have optical telescopes linked by lasers, so you don't have any kind of atmospheric impact if they're in space. So you have these optical space telescopes linked by lasers, and they can be hundreds or thousands of miles away from each other and still linked together to make one big optical interferometer. Such a system would be able to see planets around other stars with enough clarity that you could possibly tell if they have continents on them and even the color of the continents, and from that infer if they have life on them. And so that's the ultimate goal. Technologically, this is barely within our capabilities to do. So we can do it, but it would also be very expensive. So it has not yet been funded, but this is theoretically something that could possibly be done with existing technology. And so there is the possibility of extending radio interferometry into optical interferometry.